Welcome to this explainer on downhole sealing. Today, we're diving into the bridge plug and how we seal off the bottom of a well. Let's just jump straight into a catastrophic downhole scenario, okay? Picture this. You're operating a well, and out of nowhere, things start going terribly wrong. You're dealing with an incredibly expensive problem literally miles underground, and you need a permanent solution, like right now.
To really grasp the severity here, imagine your well has 3 producing zones stacked right on top of each other. They've been flowing perfectly, but suddenly, that bottom zone starts producing water, and that water is flooding in, rushing upwards, and completely ruining the clean oil production of everything above it. Your top 2 zones are getting totally contaminated. So here's the multi-million-dollar question. How in the world do you fix a flooded zone that's sitting underneath 2 miles of solid rock and steel?
Well, the reality of the situation is pretty blunt. You can't dig it out. You obviously can't just reach in and patch it up. That physical impossibility means you really only have one option left on the table. You have to send something down the hole that seals the wellbore completely, right above that flooded zone, and abandons it forever. Basically, you need to completely cut off the bottom of the well from the rest of the operation.
And that is exactly where the bridge plug comes in. It's such an elegant solution. Let's break down the anatomy of this thing, because it relies on 3 crucial components. First up, you've got the slips. These are essentially wedge-shaped metal teeth designed to aggressively bite into the casing wall and lock the tool completely in place. Second, there's the rubber sealing element, which expands to fill that annular gap. And third, a solid, impenetrable body. Literally nothing passes through it. That solid body is exactly what makes it a bridge.
So, you might be wondering, how does this thing actually set in place? It's a really brilliant bit of downhole physics. You run the plug down the hole on a wire line, and once it hits the exact right depth, a setting tool applies this massive force, squeezing the entire assembly lengthwise. Actually, it's the exact same trick used in an annular preventer. That one single longitudinal squeeze does 2 things right in a row. First, it forces those wedge-shaped slips outward along tapered cones until their teeth bite hard into the steel casing. Boom, it's anchored. But that same squeeze also compresses the rubber element. And since rubber can't compress, it has absolutely nowhere to go but out. It's forced to bulge sideways until it completely fills the gap against the casing wall. So anchor first, then seal. One single motion achieves the whole shebang.
Now, beyond just isolating a single watered-out zone, this tool actually tackles 4 main jobs out on the field. First, like we said, shutting off depleted or flooded zones so your upper zones can produce clean oil. Second, it gives operators a really solid base to pressure test the casing above it. Third, it acts as a physical foundation so a cement plug can be dumped right on top of it instead of just falling down the empty hole. And finally, it's used for permanent well abandonment, where a bridge plug plus cement legally seals a well forever.
Now, operators have a really crucial choice to make here. They can run retrievable bridge plugs, which can be unset and pulled back to the surface, or they can go with permanent ones. But here's what most people miss. Choosing between a permanent composite plug and a retrievable one actually has nothing to do with the quality of the seal. It is entirely a bet on whether the operator thinks they'll ever want to access that lower zone again. If they bet wrong and use a permanent plug, getting it out later means running a mill down the hole to physically grind it into pieces.
Let's talk about the massive technical stakes involved here, because they are huge. The number that matters most for this tool is its differential pressure rating, basically the amount of pressure difference the plug can hold across itself. We are typically talking about 5,000 to 10,000 psi. That is an immense amount of force, and direction matters just as much as the number. Some plugs are rated to hold pressure from below only, while others can handle it from both directions. If you accidentally set a one-way plug backward, well, that 10,000 psi is just going to push it right off its seat. No way around it.
But with those extreme pressures comes a really critical safety warning, and honestly, this is the biggest hazard in the entire operation. Slips absolutely need sound casing to bite into. Check the wall before you set. If you try to set a plug-in casing that's corroded, worn down, or oversized, those wedge-shaped teeth simply cannot get a proper bite into the steel.
And here is why this matters so much. If the teeth get a bad bite, the plug might actually hold perfectly fine during your initial pressure test, giving you this huge false sense of security. But later on, under real sustained well pressure, it will catastrophically slip and move up the hole. This is exactly why a caliper or casing inspection log is run before setting a critical plug. You aren't just picking a depth on a map, you are actively hunting for a section of steel casing that is strong enough to trust your well with. To really visualize how this all comes together, just think of a cork in a wine bottle. It is the perfect analogy. You push the cork in, it aggressively grips the glass walls, it seals the neck completely, and absolutely nothing gets past it. But, just like a cork, getting it out is a completely different kind of job from putting it in. You push a cork in, but you have to drill it out with a corkscrew. With a permanent bridge plug, you squeeze it in to set it, but you have to send a drill bit down to physically mill it away when you're done.
Okay, let's do a quick knowledge check with a classic point of confusion in the field. A lot of downhole tools look pretty similar. For instance, a packer also uses wedge-shaped slips to bite the casing, and it also uses a rubber element to create a seal. So based on what we've just covered, what actually makes a bridge plug different from a packer? Take a second and think about it.
Got it? The answer all comes down to the bore. You see, a packer has a hollow hole straight through the middle of it. It seals the annular space around the outside, but production can still flow right up through the tubing in the center. A packer essentially means seal the annulus but keep producing. A bridge plug, on the other hand, has a completely solid, impenetrable body. It blocks absolutely everything. A bridge plug means seal the well, nothing comes through. That solid body is the defining difference.
So what should you take away from all this? When a lower zone threatens the integrity or production of your entire well, the bridge plug is your ultimate failsafe. Using just a single axial squeeze, it anchors into tested steel and expands its rubber element to block thousands of pounds of pressure. Whether it's to shut off water, test casing, lay a cement foundation, or abandon a well forever, it is a tool of absolute finality. It is, quite literally, permanent well surgery performed on a wireline. But if an operator goes through all this trouble to abandon a zone completely, what are the long-term consequences if they ever actually need that bottom depth back? Definitely some food for thought until our next explainer.